You missed a bunch. That day to be out. I hope you get those middle schoolers the concert of their lives. Glad y'all did that. Much respect to you. We talked about 3 different types of transformations yesterday. Can somebody name one of them for me? Translation was one of them. Very good. Reflection was one of them. Last one? A rotation. Okay? Translation, reflection, rotation. Let's talk about our trigger words because those are really important. Whenever we hear the word reflection, what's the trigger word that goes with it? Flip. Reflection, flip. Okay? Whenever I hear of a rotation, what is the trigger word that goes with it? Turn. Like turn down or turn up. Okay? Whenever I hear of a translation, what do I think of? Slide. Okay? To the left and to the right, up and down. Got it? So far, so good, right? Okay? You'll need to know those for tomorrow's quiz. Yes, it's a keyword in here. Okay? The quiz will be tomorrow. It's going to hopefully be a take-home quiz. We'll go over a little bit of it in class. Okay? All right. I said this a couple minutes ago. Today's lesson is like Transformations 2.0. Okay? We'll get into the nuts and bolts of it. All of you will meet me by the time you're out here. That's my goal for today. All right? So, if you think me already, I'm already there. If not, you will soon. All right, here we go. Anytime I've got a reflection is nothing more than a flip of an image or a point or a series of points. Okay? I can reflect a couple different ways. This is the part down here that I would probably write down if I were you. If you want to write it down, somebody came to me first of all, they're like, I wrote too much today. I can take pictures of. Sure, whatever you want to do. Okay, but here we go. If anything is reflected across the x-axis, notice a little arrow notation down here. Okay, my x coordinates don't change. My y coordinates change from positive to negative or negative to positive. Whenever I say positive to negative or negative to positive, because I don't want to continue having to say positive to negative, negative to positive, I simply say pick the opposite of your coordinate point. So the opposite of y, positive y is negative y, the opposite of negative y is positive y. See why I don't want to say positive, negative, negative, positive, whatever. I say opposite. So if I have a reflection across the x, I take the opposite of y. That's simple. If I have a reflection across the y-axis, I take the opposite of x. Ah, very good. And if I have a reflection where y equals x, look what happens down here, y'all. Your original xy, your pre-image coordinates, get reflected so that your new or prime coordinate points are just the opposite of what they were written in yx form. Makes no sense, right? Let me give you an example. See if this doesn't clear stuff up. Let's say we took this here point right here, 2, 4. If 2, 4 was my original pre-image coordinate point, I would take 4, 2 as the image post-reflected coordinate point. Any questions on that? This is your first stage of rocket science whenever y'all get there, okay? So, somebody's going to make it one day. All right, a couple seconds, write this down. If you need to, I can come back later in the day, later in the semester, month, later in your life. Good. A couple more seconds. Here we go. I'll switch it up now. Now, we didn't really talk about this, but this is how I could write or draw the steps for drawing a reflection. On your EOC, you're not going to have a pencil and you're not going to say, plot these corners, yada, yada, yada. Instead, what they're going to say is, what's step 2 involved in this particular transformation? And tell me what the next step involved would be. It was really stupid and much y'all guess anyway. But, true story, right? True story. Okay, but this is how we would do it. Okay, first off, we are going to take each vertex of the figure and draw a line perpendicular to my line of reflection. What is a vertex? Well, let's keep so that, right? But I got to keep remembering all year. What? You're here, so it's probably going to be you the whole year. Probably you're going to be like that. What's a vertex? Nope. Vertex. They form a what? Doesn't have to be a right angle. It just has to be a angle. Very good. Where two lines, remember, vertex, well, let's go back to this. Angle. A line segment, or array intersects with another line segment, array. The point that the angle is formed is called the vertex. Okay? So that was step 1. Draw the line perpendicular. Ooh, perpendicular. What's that word mean? Right? Okay? So what does mean? Right angle, right on. All right, good. So I got a right angle involved here. Okay? Now, this is how easy this can be, okay? After I have formed my perpendicular lines through each vertex, I take the point that is equidistant, meaning the same distance, equal, okay, equidistant from the vertex to across the line of reflection, right? Here's a fancy way of doing that. I got my triangle. Y'all go with that? Good triangle. I got my line of reflection. I draw my perpendicular lines through each vertex. Okay? I will take the measurement and say that's 5, that's 4, this is 10. I'll take the measurement from each vertex to the line of reflection. I go 5, 10, and 4 on this side. I would get my perfect reflection. Okay? That's my perfect reflection. You're welcome. You can create your own later. Okay? But it's that simple, all right? Of course you can't freehand it. Okay? You have to know the concept behind it geometrically. Any questions on that whole process? So do you hate me? Your hatred should be about 20% right now. Okay? Not too bad. Do what? Why? Oh, we're going to do all this today. We're not done yet. 5 seconds. 3, 2, 1. We also talked about translation. Translation means what? Slide. Okay, we'll slide to the left, to the right, up or down. Right? Translation has what's called a vector. Each segment. Okay. So you don't have to know this too much. Each segment going to point and its end at the same length as the vector and parallel to the vector. Awesome. Okay. The big thing you need to know about a translation is parallel. Okay. If I tell you about a translation, how do I create a translation? I've got to be able to get parallel lines that are parallel to my original points. Okay. It's not too hard because you guys have already had slope, correct? Last year, I know y'all did. Y equals mx plus b. Rise over run is equal in pi. Over and over and over and over again. Okay? Yeah. I know. Can't forget what you did last year. Just like you can't forget what parallel means. What parallel means? Last week. What? Sitting right beside each other on the same plane for how long? Forever and ever, amen. There is no death to them apart. They are gone. There's no divorce. Okay? They are partners for life and beyond life, whenever life ends. Makes no sense. All right? Just geometrically think about it. Lines that are parallel go on forever and ever and ever. Okay? Sorry. All right? Not too bad to talk about translations. So, I think this overcomplicates things, but I'm going to go over it. If I have a horizontal translation, horizontal moves which way? Left to right, up or down? Good. Left or right. Okay. I take my x coordinate points and I either add to go to the right or subtract to go to the left. So, okay. For a vertical translation, vertical goes what? Left, right, up and down. Up and down. Okay, my x coordinate points stay the same. My y coordinate points go up if I add them, and down if I subtract it. Right on. And then I have a general translation along the vector. This is where the whole parallel line thing comes in. Okay, guys, if I move something along a vector, that means I move it the exact same slope as I have on my original line. This here point, xy, this here point, d prime, it would have the exact same slope if I moved it along the same line. Okay? I'm trying to connect some things that you just did. You've already done this when you create lines. You just didn't know it. You didn't go over it. Okay? The point of having a slope means that you are you are running along the same vector. Right? So, I'll create one of these things. Again, we won't be doing this. Guess it's just not going to happen for us. Okay, I can draw parallel lines through each particular vector, and I have made some translations going on. Okay, this is kind of that point in time where y'all have physics. You guys had physics already. Y'all gonna take physics later? I took it as a sophomore. Okay, well, sometime maybe y'all get into physics and you'll see a little bit more about how this works. Math and science meet at a certain point. This is kind of one of those points where math and science are going to meet because there's not too much geometrically we can do with this beyond the science experiment in and of itself. Okay, so we're just going to look at everything in a two-dimensional figure for now. All right. Anybody need those steps? Cool. Last thing, a rotation. All right, this has been the most difficult one for first block to understand. But you're not first block. That's right. Y'all gonna get it just fine once you listen up. Told you you're gonna learn today. What? Right. Rotation, transformation about a point from the center rotation such that each point and its image are the same distance from P. It's an all angled vertex B formed by a point and its image are congruent. What's congruent mean? Same or identical. Okay. Remember, whenever I rotate something, everything remains the same. We call that isometric, right? Or isometry, isometric. Okay. Yesterday, if you didn't know that or you didn't hear that, you go back and watch that YouTube video on the photo. Okay. Yeah. Time to do it. Okay. Rigid motion, rigid transformation means that objects keep their shape and size as I move them. Okay? It's easy to see in a translation. It's harder to see in a rotation. But everything keeps the exact same size. Congruent. It's identical. How do we do this? This has been the difficult one today. So, please allow me. First off, hear this. If I don't specify which way you rotate something, go counterclockwise. Okay? Because it's easy for y'all to remember clockwise, so in class we'll do it partway and go counterclockwise. Right? Counterclockwise. Check it out here. Let's give this XY a, let's see, 4, 2. Is that fair enough? 1, 2, 3, 4. Up, 1, 2. 1, 2, 3, 4. All right, cool. So point P was originally at 4, 2. And I rotate point P 90 degrees counterclockwise about the origin. Whenever I put that as P prime, there's a simple little trick I can do down here. I say simple, it's not that simple. My original coordinates, or my pre-image coordinates, were 4, 2. Using arrow notation, watch how this works. I take the opposite of my y coordinate point as my x prime coordinate point. Okay? For my y prime coordinate point, I use my original x coordinate point. Flip it all around and it gets all jumbled. Okay? But that's how it works. Look where P prime should be. Negative 1, 2, up 1, 2, 3, 4. Holy smokes, it works. Okay? All right. I'm going to go over that again because you're going to see that today. People are going to be like, "Stop, that is right." I'll come around and make sure to check it out for you. Right? If I start at 1, 2, 3, 4, 1, 2, 4, 2, and I rotate that point 90 degrees counterclockwise, I can simply take the opposite of the original y coordinate and then the original x coordinate, and that would represent my 90 degree counterclockwise rotation. How are we doing? Okay? Not okay? It's 90 degrees. So here's my 90 degree angle. Okay? It's hard to see because we're only doing one point. If I did 3 different points, you probably see it a little bit better. Okay? Like for a 180 degree rotation, look what happens here. If I go from point P, let's just keep the same, 4, 2. I know it's not the, this gray would probably not like that, but that's fine. This gray is so sweet, she wouldn't do anything to me. All right, if I take the original point 4, 2 and rotate it 180 degrees, trick question, what if I go counterclockwise with it? And what if I go clockwise with it? Doesn't matter, right? Same place. Okay, let's get that out of the way now. Okay. I would simply, for P prime, if this is P, P prime is simply -4, -2. Negative 1, 2, 3, 4. -1, 2. Holy smokes. That was pretty easy. Okay. If it starts negative, you go to positive. Start positive, you go to negative. Right, guys? Any questions on that one? Here. All right. Last thing. Get into good stuff. No questions on this so far. Okay. How do we do these things? What if I was going to draw these things out? It says draw a segment from each vertex point Q. Okay. Construct an angle congruent to A on each segment. Measure this from each vertex point Q. Mark off this corresponding rate to look at each vertex. Awesome. Okay. You want to do that? You want to do it that way? No problem here. This is how you can freehand all of that. All right. I'm not going to have you freehand. I'm not going to make you draw anything on the test. It's not fair. Okay. Connect the images with vertices. Honestly, I don't even like doing this because if you, you're going to be a rocket scientist. All of it. Okay. So whenever you become your rocket scientist or engineer or something like that down the road, you're sitting at Georgia Tech, get your PhD, you're going to be working on a computer with these things. Probably not going to be 3D too much, okay? But it all starts with putting it in a coordinate plane. Understand what I mean? Okay? Or get me? It starts with putting it in a coordinate plane. This is what we're going to work on today. So now your hatred should be somewhere in the 60% range. We'll see. Maybe not. Maybe it didn't triple or anything like that. Or any questions on this? Okay.